Yeah, the agenda of my talks are going to go into three parts. First, I'm going to start with some background and begin first with module performance modeling and prediction and measurement, and then follow up with the main focus, which is module durability. So in some ways, this talk will be a bridge of the first two talks this morning, the business case merged with the technical case, and understanding how those two interact. I always start off with a couple slides about Fraunhofer CSE in Boston, where I now work, because if anybody's heard of Fraunhofer at all, they think that there's exactly one of them in the world. In fact, there are 80 Fraunhofer institutes. The one in Boston is a relatively new one. But Fraunhofers are all over the planet, primarily in Germany, but they're all tasked with essentially the same mandate, which is accelerating implementation of technologies for the good of mankind. The technology space is wide, however. So those of us in solar think of Fraunhofer as being a solar-based institute. In fact, there are only two that are really focused on solar. Again, there are 80 of them. The one in Boston is not just solar, but also other sustainability issues. And the group shown there is from a picture just from a few months ago. And we're about 50 people. You can see, if you can see it at all, it's a lot of young faces, because one part of the Fraunhofer mission is educating the next generation of technologists, so we have a lot of students. So this is partially a plug for those of you in the middle of your graduate careers. We have a lot of success bringing fellows into the Fraunhofer Institutes, not just ours in Boston, but all over the world. And students work at the Fraunhofer Institutes for a period of 6 to 12 months usually, and then go back and complete their graduate studies. So that's a really fun and highly successful part of what Fraunhofer does. Just as a little footnote, it's kind of interesting in North America to think of Fraunhofers coming over from Germany and sort of colonizing U.S. and North American industries, if you will. That's not really what's going on. Fraunhofer was actually created by the U.S. Marshall Plan at the end of World War II to get German industry back on its feet. And so if any of you know Fraunhofer, it casts a pretty large shadow in Europe, and it's been wildly successful in terms of helping industry stay on top of things. In solar, we talk a lot about how we can't keep manufacturing on the continent because it's low-cost labor in Asia. Well, labor costs in Germany are a lot higher than they are here, and yet they've been able to hold on to their industry a lot better than we have in North America. And at least part of that is due to this pretty successful sort of public-private partnership with Fraunhofer in the middle, helping industry keep in touch with academic progress and bringing academic concepts into market faster. So again, in the U.S., there's 7 of these now, scattered all over the country. The one up in Boston, it's now Boston, not Cambridge, you just moved, maintains test facilities in Albuquerque, which I'll be talking about in a couple minutes. The other ones are all over the map as far as what the technology is. The most famous Fraunhofer invention is licensed out of San Jose. That's the MP3 music format. So if any of you listen to MP3s, and I'm sure you do, if you dig down into the licensing in that software, you'll see Fraunhofer's name. Fraunhofer Institute in Germany actually invented MP3. So it's a classic case of what Fraunhofer does, where they saw a need in the industry, they came up with a new technology, in this case software, and then licensed it out. So any number of industries are now making quite a bit of money off the MP3 music format. Other ones include, in Michigan, they have a couple working on automotive applications. There's a Fraunhofer that does laser ablation, for example, for automotive processes. This one down in Delaware does molecular biology. They bind various medicines to tobacco plants for creating vaccines and so on. And then again, the one up in Boston is focused on sustainable energy, of course. One more plug for Fraunhofer. This is Boston. We're in the center of an innovation district, so if any of you get to travel to Boston for conferences at MIT or Harvard, please look us up. This is meant to be kind of a local nexus for clean tech in Boston, and we just moved into this building. We were across the river in Cambridge, but we're now in South Boston. And we have this building, which is the Sustainable Energy Building, and it integrates a whole bunch of fascinating building efficiency concepts, things like phase change insulation. So you have insulation in the walls that heats or cools during the day and then releases the latent heat at night, for example. And then we're going to have solar panels on the roof and so on. So it's a renovated 100-year-old building that's a giant living laboratory and kind of fun to occupy. There are 3 Fraunhofer groups in Boston. The PV technology group is my group. In addition to that, we have building efficiency and distributed energy. So again, if this sounds exciting for any of you and you think you can shoehorn this into your academic careers, I'd recommend it. It's a pretty fun place to work. This is just my group very quickly. Expertise kind of runs the gamut. The Fraunhofer concept is to facilitate industrial implementation of different technologies, and what that means changes with time. So the Fraunhofers all have to be able to adapt. What we were doing at the Center for Sustainable Energy 2 years ago is very different from what we're doing today. But we have a good quiver of skills running from material polymer science all the way up to lifetime and reliability prediction. And the team, the green frames are the permanent staff, and the 4 gray frames are our current fellows that are with us right now. So again, offices in Boston and an outdoor test facility in Revere and a test site in Albuquerque, which is going to come up a couple times in the presentation. So getting back to PV. This is the latest data. I downloaded this from the EPIA website last night. They just released this new report for 2012. If any of you followed PV last year, there was a lot of debate whether we actually hit 100 gigawatts or not. In fact, per EPIA yesterday, the answer is yes, we did. So the world is now crested at 102 gigawatts of installed PV total, and most of that's in Europe. So this is very exciting news, but it has some interesting repercussions. So if you look at that, the uptick in PV installation is obviously huge. I would argue that PV has now tipped, and no matter what the fossil fuel industry tries to do, you really can't stop PV anymore. But what you can do is slow it down, and that's kind of the concern I think we all need to have as we try to keep PV rolling at its breakneck pace. One thing to note here is how recent most of the PV installation is. Obviously, with a very high growth rate, what that means is most of the PV out there is relatively new. And so if you go back to, say, 2009 at about 20 gigawatts, that's about where the knee is of this year's total installed capacity. So in other words, with 100 gigawatts now installed, 20 gigawatts back in 2009, 80% of all the PV in the world is less than 3 years old. And quite a bit of it was installed by companies that are probably not a whole lot older. So that's a good thing in the sense of, yeah, we've got this brand new industry that's really growing. But in terms of lifetime prediction and so on, energy performance prediction, it probably should start ringing some alarm bells. We have a lot of new companies out there, a lot of new hardware in the field that may not be the same as what people have been producing for the last 20 years or so. But nevertheless, 100 gigawatts is a fantastic number. And I'll leave it to the audience. Can anybody tell me what country uses about this much electricity? Actually, students only. Audience participation is required. No, U.S. is about 1,000 gigawatts. Yeah, the whole world is about 4,000 gigawatts, 4 terawatts. U.S. gobbles up electricity. We're at about 1,000. Okay, a little closer to home. Canada. Okay, so not quite. So Canada is actually at 130, but if you take out BC and Alberta, yeah, you're at about 100 gigawatts. So it's a phenomenal amount of electricity. So all of Canada, I mean, on a per capita basis, actually, Canada and the U.S. use about the same amount of electricity. We have about 10 times as many people, so we use about 10 times as much electricity. But 100 gigawatts is fantastic. And it's all driven by the reduction in prices that we heard about earlier in the day. So again, I think everybody knows we've been on this nice steep descending curve in terms of PV module price. And what that means is nothing short of extraordinary change in what it costs to put PV on somebody's roof. So if you go back just to 2007, I just chose 5.7 kilowatts. You'll understand why in a second. If you look on this chart, a module was about $4. This is U.S. dollars. And so it would cost you about $24,000 U.S. dollars to install 5.7 kilowatts on your roof. Today, that number has crashed down to about $5,000. So it's really quite cheap. If you think about how much a house costs, roughly $500,000 in Boston, another 5K, another 1%, gets you enough PV module material to put it on the roof. And so this is what is so exciting about PV. It really has gotten there in terms of price. I would argue, I'll talk a little more about this in a minute, I would argue that the price is going to start leveling off. We're not going to keep going downward as we have, in part because it's already so cheap. The module cost just doesn't matter that much anymore. It's a minority cost of the installation. Because unfortunately, at least in the US, you take this $5,000 worth of PV modules, it's going to cost you another $10,000 to $15,000 to actually get them on the roof, connected to an inverter, and plugged into the utility. It's still very expensive in the US to install PV on a roof. The module part is a minority part, roughly a quarter. But it's interesting to compare it to other technologies that could supplement it the same way that PV does. So with the big hurricane we had last fall, a lot of people in the U.S. went out and ran out and bought these things, including my parents, bought one of these portable diesel generators. So it's not normally what we compare PV to, but it's kind of interesting to compare a PV system that you put on your roof to a replacement diesel generator, a backup power system. So a whole lot cheaper if you went out and bought diesel to provide what adds up to about 5,700 watts, 5.7 kilowatts of electricity. That's why I chose that number. So if you buy a 6.5 kilowatt generator, you don't want to run it at 6.5 kilowatts. You run it at 5.7 because you want to have a load margin. But as I'm sure you all know, these things gobble up diesel fuel. So what does that look like? One of these things, if you buy it, will cost you about 16 liters or to fill the tank. And the tank will last, if you run it at half duty cycle, it'll last for about 11 hours before you run dry. So that works out to about 4,000 liters of diesel a year. So I don't know, what's diesel here now, about $1 a liter? Yeah. So $4,000, so great, you get a much cheaper generator, $1,500, but it's going to cost you $4,000 a year just in fuel. So already the PV is starting to look like a pretty good deal up against diesel. The real lesson there is actually not so much that PV is really cheap, although it is. The real lesson is that diesel is just spectacularly expensive. We spend a lot of money for the energy we get out of liquid fuels. Liquid fuel energy is just a whole lot more expensive than electric energy that's mostly provided by either hydro or coal plants. But if you're trying to make this kind of switch, yeah, the PV panels look pretty good. Although there are a whole bunch of reasons why you still can't pull this off because utilities won't let you island your system and so on. So, but the 8-hour-a-day thing, incidentally, as a footnote, is commensurate with what a PV panel could do. So people always come back to you and say, oh, well, you know, if I use PV panels, they don't work at night. People actually constantly remind me of that fact, which I'm actually pretty well aware of. But the thing is, a lot of mechanical systems don't run 24 hours a day either, and you can see that just in the spec sheet for this generator. And real generators, if people actually run off diesel, they have to have 2 of them, and they have to trade them because they wear out if they're run constantly. So as I just said, the case for PV is getting stronger all the time. And even when you compare it head-to-head against what it's actually having to compete against, which is grid-tied electricity. Our grid-tied system is heavily subsidized. It's amortized. It's all been paid off. We have a lot of grandfathered coal plants out there. And so electricity is very cheap, particularly in the first world. But nevertheless, PV has started to creep into grid parity around the world. So this is a chart produced by Bloomberg New Energy. And what it's showing is electricity rates around the world with the cost of electricity in dollars per kilowatt hour on the y-axis. X-axis is essentially energy yield. So sunnier countries are farther to the right. So you can see sunny areas like California, Saudi Arabia are on the right of the graph. Their electricity rates run across quite a wide range. But these lines are the grid parity lines. So grid parity is blue for 2012, purple for 2015. So what's happening is we're starting to see grid parity around the world. People ask, when are we going to hit grid parity? Well, we already have, just not everywhere. And so year over year, this line is going to creep down and down and down, and it's going to start to envelop more and more countries. And you can see it's already not too far from a good slice of the population. The size of the bubbles is the perceived market for residential PV. So we're already well within range of several European countries, the state of Hawaii, Australia. These are all areas where grid parity has already been achieved. And we're not too far from other relatively large consumers of electricity, including Turkey, Japan, and so on. So grid parity is essentially here. Back to this price chart. Specifically, PV is now head-to-head competitive with wind. And so until the natural gas boom a couple years ago, wind was being touted as the main solution because it was head-to-head competitive with natural gas before the floor dropped out of natural gas. Now what we're seeing is that PV itself has caught up with wind, and it's at essentially the same price point. That's an exciting mark for PV. It's not the whole story, of course. So this is all based on dollars per watt. which doesn't tell you nearly enough of what you need to know about whether you're going to get a return on investment over the life of a system. So the dollar per watt metric is what our industry is driven by, but it's insufficient. And it's actually creating quite a few distortions, including the price drop itself. I mentioned before that I don't actually expect us to continue on this downward trend with PV module prices for a couple of reasons. The first of which is that this is actually price, not cost, and prices have been in free fall. So this price trajectory you're seeing is decoupled from the cost of making a module. Companies, the biggest PV companies around the world, are all selling their modules below the cost it takes to make them. So the price they're commanding, it's not coupled to their cost. And being in free fall like this with the prices and saying that you're driving your price down, it's a bit like jumping off a cliff and waving your arms and claiming you're flying. That's not what's going on here. And so it's having some negative consequences too. So it's good in the sense it's accelerated adoption of PV. It's bad for at least two reasons. Number one is that it incentivizes cost over performance and doesn't give you the lowest cost of energy. So something that's cheap up front generally doesn't necessarily deliver low cost of energy over the life of the system. And it fails to take into account cost of low quality. So a lot of these makers that are selling even below their own cost, they're also cutting corners when they put together their bill of materials to make their module. And so a lot of the modules going in the field now are arguably lower quality. They're certainly lower quality and arguably have lower lifetimes than what have been built in the past. And that's going to be a problem we may pay a near-term price for. But as these factors start to get realized and captured by the market, internalized, I actually expect to see this roll off. And that's not going to be a bad thing for the industry. Again, as I mentioned earlier, it's not going to hurt us too much because the cost of the module is a minority component anyway. So a slight rise in PV modules that pays for better modules isn't really going to reduce the implementation of PV very much. But what it is going to do is give us the lifetime on which the financial return on investment is calculated. So an example of that is shown here. This is data from a program we're running at Fraunhofer called the Durability Initiative, which I'll explain later. But this just shows 5 modules. They're anonymous here. 5 modules which were plucked from the 8 top module vendors by volume in 2012. So you can get online to Photon or whatever. You can see who those 8 companies are. We're not telling you who they are because we're trying to protect their confidentiality. But those 5 modules have been put through a battery of tests, which I'll talk about as part of the Durability Initiative. They've also just been set outside in the sun in Albuquerque, New Mexico to see what happens. And as you can see, something is happening. So after just about 240 days, so less than a year, there's already a considerable spread in performance of modules that are nominally the same. They're single crystal silicon. They're different vendors, but they all have about the same rated performance. The performance is normalized to each module's rating, so this isn't a difference in predicted performance. This isn't. This should be the same from vendor to vendor, and yet you're seeing a spread. So at least 2 different things could be happening here. Anybody want to throw out a suggestion? Why are these starting to spread apart? I can think of at least 2 reasons. Probably more. I'll stand here till lunch if somebody has anything. Yeah. Well, we normalized for that. So sorry, it's not clear here, but the 100% level is actually normalized to each module's rating, so they should be able to hold to their own rating. Pardon? Okay, yeah, so in other words, they might be degrading. So my concern here is that, yeah, they're degrading. There's at least one other thing, though. They're not necessarily degrading. Yeah. In contamination, yeah. Or a little bit less accessible. It has to do with how modules are rated. They're rated under a very narrow set of conditions. They're rated STC, and one simple environmental impact that could be changing is spectrum. So when a module gets rated, it gets rated under a standard spectrum. Nobody's paying attention essentially to energy yield with the rating. The rating, again, it goes into that whole dollar per watt way of looking at modules. It's a very narrow specification. And so the other thing is that the seasons have changed. So if you really do need to wait a whole year to see if they come back up. So it's conceivable that what's happening here is that as we've headed into spring in Albuquerque, the aerosols in the air have changed. We have a bluer spectrum, for example, And so some modules with a different encapsulant may be letting less blue light through, and so their rate of performance starts to drop. So you've got essentially at least two things going on. You've got perhaps you don't really understand their performance enough yet based on their nameplate rating. And again, yeah, they very definitely could be degrading. I hope it's the first, but we're about to find out. So to get at that, you have to get into some module performance issues. And so Fraunhofer has two programs going. The most established is the durability initiative, which is the second part. But first, we also have to try to decouple these effects and try to get better insight into how the modules perform. And all of this approach is really fairly straightforward, but you'd be surprised at how seldom it's done. People know they need to do this, but again, just because of the incentives in the industry, there's just not a lot of incentive to pay attention to anything other than dollars per watt. And so some of these things fall through the cracks. Part of the reason for this is stepping back a little bit and looking at the whole industry again in terms of technology. Only really one of these technologies dominates. This chart is this confusing mix of technologies, which I'm trying to capture the whole constellation of different ways we convert sun into electricity. 3 of them are PV, so you've got silicon PV, thin film PV, CPV, concentration PV, and I've also thrown concentrating solar thermal in here. So these are all the technologies that we use to convert sunlight into electricity. By market share, though, this way of presenting the data is not nearly representative because, as I'm sure you all know, by market share, silicon PV entirely dominates. It's about 85% of all the modules out there. Even solar thermal is a relatively small slice. Concentration PV is not even worth mentioning. But one thing to take away from this is that the two at the bottom do something else that's different. The reason they're both here is because they're both tracking technologies. And I would argue that this is yet another trend that's about to have an impact on the solar industry, and that tracking has yet to be really brought in as a important part of solar. Some utility scale projects have it. Obviously, none of the rooftop projects use tracking. Tracking is going to be essential. And it's essential because it's the only way we can get above the 5 to 6% energy provision that we hear about coming out of Europe. So whereas PV capacity in Europe is sometimes 50% of the grid in Germany, it's still only single-digit percentages of the energy. And part of that is because of nighttime. Part of it's because the modules are often pointed away from the sun. So tracking is an interesting new development, and it should trickle down back all the way to the research level in terms of which technologies make sense for solar. Again, in the terms of the theme of more efficient is better, because tracking, if you buy into the argument that we need tracking to follow the sun to get more energy out of these PV systems over the course of a whole day, suddenly you're choosing different technologies. You're maybe not going for quite the cheapest technology. You're going for one with a higher efficiency because you have to pay for the tracker. So the thing with trackers is that they don't do much for you in a dollars per watt term. And the industry is, again, entirely driven by dollars per watt still. People talk about LCOE, but projects get financed almost entirely by dollar per watt concerns. And the technology choices are driven by dollar per watt too. We're just hammered on that dollar per watt number. It's why all these companies went so cheap in making their modules. It's why they might be cutting corners in terms of quality. Trackers don't help you with dollars per watt. If you add a tracker to a system, your dollars go up. You have to pay for the tracker. You have to pay for O&M. Your watts don't change. Why? Because you rate a module under standard conditions, and those standard conditions say that you're pointed at the sun. So if you try to do a system that generates more energy by adding a tracker, you're not going to get compensated for that if you're thinking in dollars per watt terms. So this simple argument is substantially the reason why tracking hasn't penetrated the market as much as it should. There are lots of trackers out there. The problem is if you ignore tracking, you get situations like this. So this was from Heilbronn, Germany, a couple years ago. This was just a picture I took outside my hotel. The beautiful thing about Germany is you can go anywhere and see solar panels. So right outside my hotel, on a parking garage across the way, it's a little hard to see, but there's this vast array of rooftop, garage top PV. This is about 4 in the afternoon. It looks kind of reddish, but the sun was well up, still well above the horizon. I think you can tell that the panels are pointed in entirely the wrong direction. So not a whole lot of energy getting generated here. And this is inevitably what happens if you're not tracking. If you get into the numbers of this, these are curves showing a particular location, in this case Palmdale, California. These are irradiance curves, so these are technology independent. This is just how much light is coming into your surface. if you're not tracked, if you're using fixed tilt, meaning tilted usually at local latitude, or horizontal, this is the amount of radiance you get to deal with. The taller peak is the fixed tilt, the shorter, darker gray peak is horizontal. So not surprisingly, when you're lying flat on the ground, you don't get very much sun in the afternoon when the sun is moved closer to the west. How bad is it? Choose 4 in the afternoon here. So if you have a peak rating if you have 1,000 watts of radiance coming in per square meter at midday, at 4 in the afternoon, you're down to less than 400. So your solar panel, if it's rated at 200 watts, it's going to be at 40% of that at 4 in the afternoon. So if you're trying to make PV an important part of the grid, it's really not going to work without tracking. So the fact that we've got all this capacity out there that's not tracking tells you we've got a bit of a problem. If you fold in tracking, things start to look a lot better. The blue line up here is actually just for reference California's electricity demand. So obviously, again, the demand, unfortunately, doesn't peak in the middle of the day. It peaks in the late afternoon. So solar technologies, no matter how efficiently they convert, they're still stuck with this daylight curve without storage. But adding tracking really fills out those shoulders pretty nicely. So you're still not able to run all day, but you get a much squarer profile so that now in 4 in the afternoon, you're at more like 60 or 70% of your peak. So tracking is a major boon in terms of getting more energy out of your system. If you fold in efficiency, and this is sort of a plug for CPV, things get even better. So the efficiency curve changes the dynamic considerably and really boosts up anything that is high efficiency that can justify 2-axis tracking. So the best form of tracking, of course, is 2-axis. To be able to pay for that kind of tracking, you pretty much need high efficiency, which backs you into CPV. So if you go that route, you can get a much more energy per dollar installed. So in terms of how we analyze this, I'll stick with CPV for a second just to use as an example. So this is a structure of a multi-junction cell. We have to start to be able to model and figure out, okay, exactly what am I talking about? I know it's going to be better if I pay attention to spectrum and tracking and so on and look at energy, not just watts. But you got to try to get that analytically. So for a multi-junction cell, they're extremely sensitive to spectrum variation. So it happens to be an area where you can get away with paying more attention to spectrum because you have to. So again, the standard spectrum looks something like this. The 3 junctions in a typical 3-junction multi-junction split up the spectrum into 3 parts: visible for the top cell, near infrared for the middle cell, and more near infrared for the bottom cell. That's standard spectrum, and that's what everybody tunes to. That's what every module's rated to. If you go to Las Vegas and look at it over the course of a year, it's much uglier. So this gray mess is a series of spectrum curves for a whole year in Las Vegas. And you can see that, I hope you can see that not only does the amplitude change, but the shape also. So there are times of year, particularly down at the bottom, where pretty much all that blue goes away. And if you're still trying to get energy out of your system, the top cell is going to shut down because they're series connected. So with multi-junction cells, you get a particularly high dividend by paying attention to spectrum. But the dividend for other technologies is there as well. So we're going to be looking at trying to figure out whether we can predict this and tune modules accordingly. There are several ways of approaching this. One of them is shown here, where we have, thanks to NREL, we have a nice spectrum generating model where you can take, for example, typical meteorological year 3 conditions, which are laid out in a table from NREL also, and plug those conditions into this model, and it'll spit out a spectrum for you. And so it's important to go back and check that that spectrum actually represents what you get at a given location. But we've done a lot of that and found that it is actually quite predictive. But the approach is essentially to generate those spectra based on a given set of inputs, and then you can get this field of spectra, in this case from 300 to 1800 nanometers, and throughout the whole year at a given location. In this case, this is again for Las Vegas. This is modeling I did when I was at Amonix. So this then convolves the spectrum shown on the left with the multi-junction response and the optics losses and so on for the particular CPV system that Amonix makes. And then you get a graph that looks like this. So now the spectrum is kind of split up into its component parts. And then you can look at how much current you're going to get out. There are 4 ways to verify this. So what I just showed on the previous slide was an example of predicting the result. And people typically use the terms predict and expect interchangeably, but there's a subtle difference between them. So if you take data from a database, plug it into a model, it spits out a spectrum, and then you apply that spectrum to your hardware and get a performance result, that's predicting the result. You can actually do that, look forward. You can say, I know what it's going to do on January 5th, 2015. That's true prediction. Most of what people do is expected results. They'll measure the irradiance. They'll measure the temperature on a given day and say, okay, if the temperature, I've measured the temperature of 40 degrees C, the irradiance is 1,000 watts per square meter, I know my module will put out 225 watts. That's an expected result. So keeping those separate is very useful because obviously prediction is the much more leveraging approach, but it's also harder to get right. Expectation helps you verify that prediction. And in this case, for multi-junctions, we have two ways of doing expected results. So you can do expected by measuring atmospheric variables, feeding those into smarts, and getting a spectrum. We've done that. And all of these are shown on the chart on the right. You can also take expected direct by measuring the spectrum on site directly. And then finally, you can use isotypes. Isotypes are just the subcells broken up into their component parts. You can look at each. So each one's like a broadband absorber. And you can see we did this for Vegas, and they all overlay each other rather nicely. So prediction, two different ways of expecting, and then measuring all give essentially the same result. It's a very leveraging result. It means that if you do things right, you can actually get back to prediction. The main thing here is to try to verify the gray lines in the back. These are the things we can take to new sites before we've had a chance to measure and have an understanding of how our system's going to function. It gives you some nice insight into how things work, and it's not always intuitive. Looking at Vegas again, if you model this and do a predicted direct normal irradiance, the amount of light coming in, it's this nice smooth dome. So you might expect that peak power would match the peak irradiance. That's usually how it works. In fact, your prediction shows something quite different. Because of a combination of temperature, which is fairly obvious, but also that spectrum, we get a dip. So just where we'd expect highest power because we have the highest irradiance right in the middle of summer, it gets hotter and the spectrum shifts. The air gets denser, less infrared gets through, and so the cells drop in performance. And so the combination of the factors creates a saddle which we've seen explicitly in real systems in the field. And it's something you wouldn't know unless you took spectrum into account. Temperature is a relatively easy thing to correct for. Spectrum's a little more sophisticated. And so these charts show exactly how predictive it is. Again, the gray in back shows the up and down of the predicted result. And the gray does take in one correction, which is rainfall and cleaning. So that's something you can't predict ahead of time. So unfortunately, it's not quite a perfectly clean prediction. You do have to correct for cleaning. But other than that, it really is a pure prediction, meaning we took the TMY3 database, fed it into smarts, modeled the system's response, and got these series of delta functions showing what we expect the performance to be. I hope you can see it, but the actual measured response over 3 years matched up really quite nicely. So outdoor real measurements in the field overlay with what we predicted rather well. If you roll all this up into cumulative energy, it gets even better because that takes out the fundamentally unpredictable things like cloud cover. Those get averaged in. There's an average cloud cover that comes out of TMY3. And then you can get a prediction that after 3 years of running this was within 1% of actual measurement. So at least in a desert site, you can do, to my mind at least, a pretty amazing job of predicting how a system's going to perform years ahead. So other than the cleaning factor, which in cumulative energy you could actually just average in also. If you said you're going to clean 4 times a year, you can come up with an average cleaning rate. I could have essentially predicted the output within 1% 3 years in advance. And so that is, of course, pretty helpful if you're trying to figure out what your return on investment is for a PV system. So the question is, can we extend this to other technologies? So I was with Amonix. I've left Amonix. I'm now at Fraunhofer. We're now trying to do this for the greater PV industry at large. And we're kind of taking a whole hog approach. So we're throwing out into the field a lot of different variables. Again, with the irradiance and spectrum, we're going to be trying to predict it. We're going to be doing expected results by measuring aerosols and, of course, measuring it. We're also going to have tracking and all flavors of tracking, too. So you want to understand whether a module's performance is falling off just simply because it's on a rack versus a tracker. So we'll have latitude tilt, fixed, no tracking, single axis, and dual axis. Cost effectiveness of dual axis with silicon modules is suspect at best, but what it gives you is kind of the ultimate performance. You can put it on a dual axis and you say, okay, this is as good as it gets, and use that as kind of your baseline. And then we'll be looking at all the different technologies. We've started just with single crystal just because that's what we had on hand, but we'll be adding in polycrystalline thin films and even some CPV. This is the test site in Albuquerque. You can see we have an array of different setups, mostly fixed racks. Over here is a Soitec tracker. And it's very sunny there. So we're just getting started on this, just preliminary results to show as yet, but it gives a flavor for what's coming, hopefully. You can start looking at predicted, expected, and measured, and already we're getting interesting results. The predicted, again, comes from this TMY3 database. It kind of hums along smoothly, expecting relatively high DNI. We hadn't measured in red DNIs nearly that high until about a month ago, and then suddenly we got this pulse of higher DNI measurements that lined up very nicely with the predicted. So there's some kind of anomaly going on here. The middle solution is the expected DNI. That comes from a sun photometer, which measures the aerosols. Expected and measured matched really nicely at first, but then we lost it right here. And we don't have expected results yet. So it'll be interesting to see whether the expected results rise also, as they should, or if we start to see any differences. So this is a little less well-behaved than what I saw when we did this in Vegas a couple years back. And we'll have to continue tracking that. And of course, we're also doing global, horizontal, and so on. So it's going to be a lot. It's going to be a big data management exercise. But there's a lot of information in there, and I expect we'll be able to find some useful design changes for the modules coming out of what we learned. If you compare the modules, all I've got here so far is dual axis and single axis. Again, the sample rate isn't very high, and you don't exactly care about power that much anyway. What you really want to find out about is the energy yield, and that's not shown here yet, but we're working on it. But already you can see cases like this one right here, where on this particular day, for this particular module, having it on a single axis tracker was no worse than having it on a dual axis. So obviously, as you get closer to summer and the sun is higher overhead, the dividend of putting a module on a more expensive two-axis tracker is moderate at best. And in this case, it was negligible. But on the same day, for the other technologies, there was a bigger difference. And so is that significant? Does it have something to do with contaminants or dust on the module? We'll have to find out. But it's only by studying this in detail that I think we'll get the answer. And to squeeze a few extra percent in energy out of these systems can be highly leveraging. It goes straight to the bottom line, return on investment of a system. So, a 0.1% may not sound like a lot to most people, although it's starting to now. But if you're talking about 25-year return on investment, that can be the difference between making and losing money. An even bigger lever for making and losing money is the durability of the module. So again, I'll go back to this chart for a moment. The great news about such a rapid rise in module deployment is offset a little bit by the fact that so much of the module manufacturing is new. And so from a durability standpoint, that's a scary fact. This is backed up by a fair amount of work that's been done. This has largely been done by the National Renewable Energy Lab out of Golden, Colorado. They've looked at modules over the years and found some rather unsettling changes going on. So if you look at the blue, that's the most recent modules to go out in the field, and their degradation rate per year in tenths of a percent. Typically, for most financial models, people tend to assume degradation rates of around 0.5%. So if you look at this tail here, you can see quite a few modules are degrading faster than that 0.5 most people take for granted. If you go back in time, it gets better. So the graph at the front is actually from older modules. So if you go all the way back, the faint green is the oldest modules we have records for, going back 20 years. The tail isn't nearly as significant, and the mean degradation rate is lower, which it'll be clear on the next slide. So again, there are at least a couple possibilities for what's going on here. Number one, I guess you could assume that only good modules have been kept, which isn't actually a bad assumption, right? Like if a module breaks or degrades, people might throw it away. Although a lot of these are coming out of places that are studying long-term degradation, so that's maybe not the greatest conclusion to draw. Of course, the other conclusion would be that the newer modules are degrading faster, and they're not the same. This is not at all a trivial conclusion. Most financial modeling, which our industry depends on, is based on the assumption that they understand what the degradation rate. And most of those long-term degradation rates are from long-term modules. So if new modules aren't represented by the older modules, we've got a disconnect. And unfortunately, it's a disconnect in the wrong direction. If you break it up by technology, it becomes even clearer. So INREL's taken this and broken it up by all the different technologies. The first thing you notice, this is essentially like taking that graph and looking down on it. The mean for silicon is much better than the rest of the field. So these newer technologies, amorphous silicon, thin films, they still have much higher degradation rates. And so that's not terribly surprising based on the additional maturity that silicon leverage. But the other thing is this tail. And so the question is, how does this tail relate to installations? You know, if 90% of the installations out there, that 100 gigawatts, are made from the high-end modules, the ones with low degradation rates, we don't have much to worry about. But what if most of the volume comes from this tail? Now we've got a degradation rate which is far exceeding anybody's financial model, and this is what people are going to hear about. When they think about PV, they're not going to hear about the science experiments, the low degradation modules that are relatively low volume. They're going to hear about the high volume modules that everybody has in their fields. And so I can't answer the question of which modules are preponderant in the world, but you can guess, right? If there's a connection between the higher degradation rate and cost, you can guess that the preponderance of modules out in the field are the cheaper, lower quality ones. And that's what we're worried about. Switching away from NREL to SunEdison. SunEdison is a major third-party installer of PV arrays, primarily ground mount. They've broken up their failure rates. So they've got enough megawatts in the ground that they can actually start to see significant statistics in terms of how they fail. So when we talk about failures of a whole array, number one is very much still the inverters. Modules are actually pretty negligible. So this is sort of a little bit more comforting. If you're alarmed by the previous slide, this slide should make you feel a little better, because the failure rate at the module level is really rather minuscule compared to the failure rate of the rest of the system. Again, inverters really dominate failures in the field, and this is something to consider with microinverters, for example. But the total number of failure rates in any case is still quite low. So they've got several hundred megawatts now under their management. This report, which is 2 years old now, only had 3,500 reports, and which came from 350 systems. So in other words, they had a lot of failures coming from a relatively small number of systems. If you drill down into the module rate, which again is quite low, this is the distribution by component. So the most common thing is the glass. The glass breaks. It either gets cracked when they install it, or a bird hits it, or a hail strikes it, or somebody shoots a BB gun at it. But the other failures are non-trivial. Cells, pretty much everything fails at some level. Cells, backsheet, the MC connectors they clip them together with. Other is always a good category. I'm not sure what's left here. But junction box, cables, and the bypass diode. Bypass diode, to go off on a tangent, nobody really checks the bypass diode. It's just assumed to work. So failure rate is likely to be higher. Because as they say here, there's a detectability issue too. These failures are just ones people have observed. They have to either see a drop in power that causes them to walk through the plant and look for problems. That's annoying. It's one of them. Yeah. Speaking of failure rates, I'll try. I'm probably loud enough without it, right? Okay. Can you guys still hear me or not? Yeah. Oh, I don't know. Let's try it again. So last bit of sort of context data. This shows a bunch of published reports. Again, NREL collected this data. Looking at the degradation rate published versus the warranties. So the red line is the gradual stepping up of demand from the industry. As time went on, the industry has demanded or been pressured to provide longer and longer warranties, to the point where 25 is shown here through 2010. I'd say it's probably moved to 30 by now. 30 is becoming an increasingly popular number. So people more or less arbitrarily provide longer and longer warranties. How much data is there to justify any of these warranties? That's shown by the blue dots. So for every publication that has a particular degradation rate, you can see there are very few publications that show degradation that's slower than what the industry is asking for. In other words, there's a large body of evidence showing that degradation is higher than what people are warranting. And you know, up until 2 years ago, people shrugged this off and said, well, we'll just invest in big companies. That's how the first tier came about. Essentially, it was a flight to large companies. saying, well, the company, even if we have a problem, the company's growing fast enough, 200 megawatts will be nothing 5 years from now, so they'll be able to pay for the replacements. Well, there are a lot of knock-on effects to that, and of course, as we've now seen with SunTech, companies don't always last as long as people expect. So all of this is a build-up towards a perceived need to do something about this problem. Before the PV industry gets painted with a broad brush and shown to be suspect, we need to step up as an industry and show that we understand this problem and we're addressing it. So this is something people talk about a lot, but there's only been limited work done on it to date to address these problems. Everybody sees these problems, chats about it, but it's like the weather, nobody really does much about it. But there have been several initiatives now to try to address it. One of them is the Fraunhofer Durability Initiative, which is the data I'll show from here on out. So the point is that even though all of these modules I've been talking about and somewhat trashing, they've all gone through qualification. They've been certified. So the certification tests are inadequate. You can't just have a pass-fail test and say, okay, this has passed a standard set of tests, it's going to last 25 years. There's no connection between a certification pass-fail test and lifetime. And no one that even does those certification tests would claim that. However, there is a perception that if it's certified, it's going to be good. That's not sufficient. Secondly, what little data there is held confidential. No company that knows its modules are degrading is going to tell anyone. So you have to rely on entities like SunEdison to start publishing the data. And even when they do it, they have NDAs, and so you don't hear whose modules were actually causing the problem, except by hearsay and gossip. So there's a need to find a way to get information out there more than we have in the past without upsetting the apple cart and getting everybody panicked about their confidential information. So that's led to this idea of a rating system that will allow us to compare different modules. They all pass qualification. We want to see which ones degrade faster. Again, the Durability Initiative isn't the only effort. There's also this large PV module quality assurance task force being created to address a host of degradations. I really put this up here to just show you how many ways things can go wrong. This one on the top is hard to see, but it's actually rooftop ballasted arrays that have flipped over in the wind. That's not good. And in terms of their irradiance, upside down is a really bad way to absorb light. This is a thin film module which has the classic moisture ingress problem. So you can see, I think, that around the edges, moisture is getting in, and that's going to severely degrade that module. Neither SIGs nor cad telluride handle moisture at all well. And then the final one is actually a CPV module. So what we're trying to do with these durability approaches is actually get into wear out. So I think this is a familiar curve to everybody, the bathtub curve. And so most qualification takes care of this problem, the blue infant mortality problem you have initially. After that, you expect random failures over the course of the lifetime of a module or a slew of modules, which means that essentially for every time period you get the same degradation. So if you were trying to accelerate this, if you put a bunch of modules in a chamber and 5% of them degraded, if you put them in for 100 hours, put them in again for another 100 hours, you get another 5% degradation. It's a nice, predictable, random failure rate. What we're trying to reach is wear out. We want to find the lifetime. So we have to stress the modules to the point where the actual degradation rate starts to go off a cliff and accelerate. So the idea of the PV Durability Initiative is something of a threading a needle type approach where we're trying to get more information out there, but also make sure people want to participate. If we disclose everything about the module and name names, we'd find very few people signing up for, and in particular, of particular importance to us, paying for the testing. So unfortunately, we can't subsidize this test ourselves, so we need people to participate. Most people who have access to the modules, one way or the other, have a vested interest in those modules, including people that have bought them. So if they have a big project, they may already have contractually committed to using those modules. Not easy for them to back out. They want to get information about them, but they don't necessarily want a bunch of bad publicity that's going to cause their financiers to run for the door. So there's it's a delicate balance we have to strike. We've got to get people to participate, but still get as much information out as we can. So we've come up with a rating system which essentially anonymizes the data. So if you join the program, you get feedback, you see how your module rated against the others. You don't get to find out who the others are. They're anonymous. And vendors have the option of announcing. So the idea is that if you do well, hopefully people will be incentivized to attach their name to the results. And over time, those whose names don't show up on the list are sort of guilty by association. Their absence is noticeable. So there's definitely a pressure there to eventually get the names out there, and that's, of course, what we really need. So it's a combination of accelerated and outdoor testing. I showed the outdoor data already. It's third party. We're trying to be as neutral as possible with this. And it's meant to be kind of a Unix-based approach. We have a protocol that we're running. It's not meant to remain only the Fraunhofer Durability Initiative. We're hoping other people will implement something similar, and it'll eventually become part of a standard. But if any of you know standards take often about a decade. So we need to get this data long before a standard's available. So the people that participate get a lot more data than what I'm going to show. But what I am going to show is the results from the first set of modules. And this is the portion of the data that's kind of been anonymized, normalized, so that you can't tell which technology is involved. These are all the tests. The detail isn't terribly important. They're fairly familiar reliability tests, just driven a little bit harder to try to reach that wear-out regime. We have again, somewhat arbitrary rating scale that has greater density of ratings near the high end because modules don't degrade very fast. And then to get a 0, you pretty much have to have a dead module. So this is the roll-up. We test these for both performance and safety, but I'm just showing the performance data here. And so all the performance data has been rolled up so that you can't tell whose is whose. And you can see, though, what's interesting, again, these are 5 of the top 8 module manufacturers. There is a range. These things did not all turn out the same. You can see in particular under dynamic load, one of the characters got a 3 on the scale, which says that they were below 88% in their testing. So again, these are modules that are nominally the same. People think of them as commodities that are interchangeable and distinguishable only by cost. This data would tend to challenge that idea. The one manufacturer who's chosen to announce themselves is the one that got really high ratings, and that's SunPower. So SunPower has announced who they are. They're PVDI 01. And they have a little A at their name because those modules weren't bought on the commercial market. SunPower doesn't sell their modules on the commercial market, so we had to buy them from a wholesaler. So they're less scrambled than the other modules, so that's an important qualifier. I'll just run through these tests rather quickly. They're here just for illustrative purposes. This is PID. It's an important test. Everybody denies that they even have PID. There are a number of mechanisms that can cause potential induced degradation. These are starting to show up as system voltages keep going up. So whereas a few years ago, nobody was above 600 volts, most European systems are now at 1,000 volts. And so that voltage is essentially a potential energy that can cause a lot of interesting mechanisms to activate. There are at least 5 different failure mechanisms associated with PID. And so we'll see with these modules, they have different susceptibilities to them. One key point with PID, and SunPower is the orange one, and they've for many years known that they have PID under positive bias without illumination. This is all kind of an interesting illustration of the need for combined effects testing. Unfortunately, one of the problems we have with these tests is that they're usually fairly simple and easy to manage. And so if you do potential induced degradation in the dark, a module will behave differently from when it's illuminated. Of course, in operation, the module is not going to see a potential unless it's illuminated. So in this test, we can't really get illumination into our test chamber, so we do it at the end. And so for the SunPower module, you see degradation as expected, but it recovers after the illumination part at the end. So ideally, if we did this test right, we'd have illumination in the chamber, and then that module would probably never degrade, although we'd need to see that. That's unconfirmed. All we can say is that it did recover once we shined light on it at the end of the test. In negative bias, that's the much more common PID failure mode. There are, again, 2 modules from vendors who claim not to have PID issues had PID issues, and they did not recover. So that's something of a red flag. Degradation was substantial, 80%. Damp heat UV was one where we didn't get much, so I'll just skip over that. This was a test we didn't hit it hard enough, and so we didn't reach wear out. With performance ratings, we're now in dynamic load and static load. It's kind of hard to see here, but we saw a much more significant difference. Static load and dynamic load are meant to represent snow load and wind load, respectively. And again, we had a break, where if you look down these columns, we had 2 different modules which actually degraded rather substantially under these loads. And they're not supposed to. Finally, thermal cycling, arguably the most conventional test there is. Again, pretty significant degradation in 2 of the designs. Not all of the modules degraded. We had 2 that more or less held their own, but 2 of the 3 modules put into the test failed dramatically. So are these modules commodities? Not exactly. So last slide is the outdoor testing again. It kind of brings us full circle to show that what those tests show you can inform the outdoor data. So this work hasn't been done yet, but now based on the degradation we've seen with accelerated testing, we can now go back and see this outdoor testing and get a better sense of what's going on here. And that's the eventual goal of the program, is to be able to get true predictive power for how these modules are going to perform in the field and separate the good from the bad. We need to be able to show the world that there are robust modules. They may cost a little bit more, but that money is worth it in a 25-year lifetime. Thank you.